This video is for topic 9 of the Edexcel GCSE in Astronomy. And in this video, we're going to be looking at exploring the moon. This video contains content from the specification that is examined in paper 2. These are the 5 topics we'll be looking at today. And you can see it focuses on the moon, but 9.4 is more to do with how you get into space with rockets. So I'll be covering that a little bit as well. Starting with the internal structure of the moon. As you can see here, it looks very similar to the internal structure of the Earth. There is a core made mostly of iron. That iron core is solid with a partially molten zone around it. The Earth's core has a liquid iron region around it, an outer core. And then where the Earth has a mantle, which is mostly solid, but it's sort of a semi-liquid solid state. The mantle of the moon is mostly solid. And then both the moon and the Earth have a rocky crust. Now, this diagram doesn't quite show that mantle of the moon is partly liquid, just a little bit liquidy towards the middle. There are 2 sections to it. One of the big differences here is that the crust thickness is different on the moon on one side compared to the other. The side of the moon that's nearest to us, the Earth is only 31 miles thick, whereas it's 40 miles thick on the side of the moon that is furthest away from us. But just taking a slice through the Earth and comparing that to the moon, we can see that the layers are very, very similar. There is a solid core in the middle, made mostly of iron. Then there's an outer core, which is liquid iron. And then there's a region of mantle, which is sort of a little bit fluid. Then there's a bit of a more solid layer. Now, for the Earth, that solid layer is the crust. But for the moon, that solid layer extends quite a bit deeper. The upper mantle of the moon is mostly solid. And the crust of the moon is this igneous rock. One of the ways we determined the internal structure of the moon is by observing how the moon rotates, as it librates, and using fluid dynamics to model that sort of motion. By doing that, we figured out what the inside of the moon looks like. There are also gravity sensors and things that are on probes that orbit the moon. So let's compare the near side of the moon to the far side of the moon. Obviously, we've already mentioned that the crust is far thinner on the near side. The picture on the left shows the near side of the moon. The picture on the right shows the far side of the moon. Sometimes the far side of the moon is called the dark side, but that's not because it's dark. It's just because it is obscured from our vision. So the word dark there doesn't mean darkness in the traditional sense. Each side of the moon has about 50% sunlight. And what you can see on the picture on the left for the near side are these large black regions, which you don't see on the far side. Those black regions are there because the rock is newer, it's less old. So there are fewer craters in those regions because the rock has been refreshed, renewed by fresh liquid rock being deposited on the surface and then solidifying, freezing. That hasn't happened as much, anywhere near as much, on the far side of the moon. Apart from perhaps this region here, you can't see any of those dark patches the same way you can see on the near side of the moon. One of the reasons they're dark is because it's a slightly different rock. The albedo of that rock is lower. Albedo is the term we use to describe the reflectivity of the surface. Well, that means that there has been tectonic activity on the moon, depositing fresh lava on the surface of the moon that solidified to form these basalt maria, these seas that I spoke about in a previous video. Now, if we look at this map of the moon, you can see those different regions. One side of the moon that you can see here, where it's mostly blue, those are those rocks which are freshly deposited. And then the other side of the moon, which looks far more orange here, the older side of the moon, the older face of the moon, it's got more craters on it. The picture on the right here is just showing some tectonic activity, showing lava rising up through the cracks in the moon. Now, we don't see that anymore. The moon has cooled sufficiently and the outer mantle is sufficiently solid that you don't see this anymore. Of course, we still see this on the Earth, so we can look at what happens on the Earth and extrapolate that to what we might have saw on the Moon many, many, many years ago. Millions of years ago, billions of years ago, perhaps. Now, the far side of the Moon, of course, we can't see. Actually, we can see 18% of the far side of the Moon due to lunar libration, which, of course, I talked about in a previous video. But most of the far side of the Moon is invisible to us because of the fact that the Moon is tidally locked. So we always see the same face of the Earth. The Moon takes exactly the same amount of time to orbit the Earth as it takes to rotate once on its axis. So how do we have information about the other side of the Moon, the far side of the Moon? And that's where the aided astronomy comes in. We can't see it with the naked eye, so we need to use something else, something to aid our observations. Well, here is the first photograph taken from the far side of the Moon. And you can see that large spot here I mentioned before. It's there on this photograph. You may not be that impressed with the look of this photograph, but I assure you it is very impressive how this photograph was taken. Back in 1959, this Soviet probe orbited around the Moon a few times. Now, while it did that, it managed to take photographs. And now, today, we use digital cameras, and the idea of taking a photograph and beaming the data from one place to another, we don't really think about. It's so easy to do. Back in 1959, that wasn't the case. There are a number of challenges. For example, if the probe is on the other side of the Moon, there's no direct line between that probe and the Earth. So you can't send a radio signal directly between the probe and the Earth. But that means that, firstly, you can't send the signal from the photograph until you see the probe again. But secondly, you can't control that probe. You can't be choosing when to take your photograph. The probe has to decide when to take its photograph itself. In 1959, computing power was not what it is today. So the idea that in 1959 they were able to design a probe that was able to take photographs of the far side of the Moon and beam them back, automated, is an incredible idea. Now, just taking a photograph of the Moon on Earth through a telescope, you'll appreciate how challenging it can be. The Moon is very bright. So trying to take a photograph of the Moon means you've got to adjust certain camera settings, the size of your aperture, the exposure time, that sort of thing, to try to capture the detail you want from the lunar surface, from the lunar disk. So if you're orbiting around the Moon very quickly, you want to time it so that the sun is illuminating the far side of the Moon when you're trying to take those pictures. So you have to have some way of detecting where the sun is, where the Moon is. Once you've decided that it's the right time to take your photograph, then you have to take the photograph. So there's the camera shutter that operates. And you're going to want to take more than one photograph in case the first one doesn't quite turn out. So there's mechanical parts involved there. Now, back then, the way photography worked was a photograph was taken exposing a piece of photographic film. Light was focused onto a piece of photographic film that then had to be developed. You can't bring that film back to Earth, so you have to develop it on the probe. And then somehow you've got to take that film, that physical photograph, it's on a film, not on a piece of card like other photographs are, but it's still a photograph. You have to take that and somehow transmit the information from that back to Earth. And there weren't any digital cameras. Scanners, the way we know them nowadays, didn't exist. So they had to be invented. So the way the spacecraft knew when to take the photographs and how to point the camera is it had various photocells. Photocells generate a voltage across them when they're exposed to light. So they had two cameras taking pictures, and then those films had to be developed, which meant the film had to be dipped into the solution. Well, this is in microgravity, so that's going to be challenging. And then had to be dried. Everything had to be dried. So then you've got these little films which you want to somehow send that picture back to Earth. Very, very clever how they did that. In order to get that picture back to Earth, they had to invent a scanner. And the scanner worked by having the film having a dot of light passing through it. Now, in that film where it was darker, less light got through. So they then had a photomultiplier tube underneath, which amplified up that signal, and then they just sent that signal as an analog signal back to Earth. So as the dot moved across the photographic film, it sent the signal of how bright the light was that passed through it. And then that signal was collected on Earth, and then they reconstructed the image, playing back the signal and using it so that when it was brighter, they knew that it was a clearer piece of the film, and reconstructing the image that you can see here, the first ever photograph of the moon. Incredibly clever. Because the issue was that there weren't any humans on board that Soviet probe to choose when to take the picture, to focus it, to make the adjustments, to take the film out, to process it. There's no one to do that. In 1968, the Americans sent the Apollo 8 mission to the moon, the first mission to visit an astronomical object. Apollo 8 reached the moon, orbited the moon. On Christmas Eve, they took communion on the far side of the moon, read from the Bible, the first 10 chapters of Genesis, which was broadcast live on TV, and they took photographs. They, with their own eyes, saw the far side of the moon for the first time. You can't say that's not an aided observation. So how do they get there? Well, this is where rockets come in, and an idea called escape velocity. Now, the mathematics I'm going to show you is A-level physics. You do have to know about escape velocity for your GCSE, but perhaps not in quite as much detail as I'm going to show you here. Escape velocity is how fast a body would have to move in order to never fall back to Earth. So imagine if I'm throwing something in the air, I expect it's going to land back on the Earth. If I throw it faster, then it gets slower and slower the higher up it goes, and then it will fall back to Earth. If I throw it even faster, it will go even higher before it falls back to Earth. But the further away from the Earth an object gets, the weaker the gravity is. So if I'm able to throw this object fast enough, then it slows down, but as it slows down, gravity gets weaker. So its attraction to the Earth gets weaker. And if I throw it fast enough, it can be that it never slows down enough to actually stop and fall back. And that's the escape velocity. So to calculate the escape velocity, we use two equations. We use the gravitational potential energy equation and the kinetic energy equation. Now, the kinetic energy equation you've seen loads of times, I'm sure, but the gravitational potential energy equation that I'm showing you today is a bit different from the one you might have met. You've probably met the equation mgh for gravitational potential energy. Actually, that's not quite correct, because the equation E equals mgh assumes that g is constant. G is the acceleration due to gravity, the gravitational field strength. In fact, it's not constant. Gravity gets weaker the further away you go. So I've got here an equation, V equals E over m. That's an equation for gravitational potential. It is the amount of work done on a mass, bringing it from infinitely far away to where it is, divided by that mass, so per unit mass. So for example, bringing a kilogram mass from infinitely far away to some position, it got, 63 million joules of energy in doing that. So it's gaining kinetic energy as it falls towards the Earth. It means it's losing gravitational potential energy. And so if we say initially it had no gravitational potential energy, 0, when it's infinitely far away, then the closer it gets to the Earth, that gravitational potential energy becomes negative. And that's why this equation for potential has a negative sign. The gravitational potential is equal to this constant, g, called the constant of universal gravitation, or the universal gravitational constant. It's got this thing here, big M, that's the mass in our case of the Earth, and it's got this thing r. That's how far from the centre of that mass, in this case the Earth, we are looking. The gravitational potential multiplied by the mass of the body that we're considering, so our 1 kilogram mass in this case, is equal to the potential energy. And it's negative. Let's say I'm 100 kilograms, and on the surface of the Earth, my gravitational potential is negative 63 million joules per kilogram. then that means I have negative 6.3 billion joules of gravitational potential energy right now. As r gets bigger, as I get further away from the Earth, this number gets smaller. Therefore, the gravitational potential energy becomes a smaller magnitude. And so that's why I gain gravitational potential energy as I increase my distance. My gravitational potential energy is becoming less negative. My change in gravitational potential energy as I move further away from the center of the Earth is positive. But gravitational potential energy as an absolute value is negative. Perhaps I shouldn't use the term absolute value there, because often that means the same thing as modulus. So if I equate these two equations and then rearrange, my equation for gravitational potential energy is this. That means I have to gain minus this kinetic energy in order to reach infinity, to get away from the Earth. And so I just multiply it by -1, and I get this. That's how much kinetic energy I need in order to escape the Earth. Kinetic energy is half mv squared. So if I equate these two, you'll see the small mass will cancel, rearrange to get v as the subject, that's the speed, and my speed is now this. Square root of 2gm over r, where g is the constant of universal gravitation, m is the mass of, in our case, the Earth, r is how far away from the center of the Earth we are, and v is the escape velocity. Be careful, because I've got a little v here and a big V here. So little v is the escape velocity. So what's the escape velocity at the surface of the Earth? How fast would I have to throw a cricket ball on Earth to get it into space so it never falls back to Earth? Well, it's not quite as simple as that, because obviously there's air resistance. But let's keep it simple. If we do that calculation, it works out to be about 11.2 kilometers per second. I cannot throw a ball that fast. 11.2 kilometers per second. If we were able to throw something at 11.2 kilometers per second, that's about 25,000 miles per hour, directly upwards, and there were no air resistance, it would arrive in space and never fall back to Earth. But the escape velocity, as you can see in the equation, gets smaller as the distance between the center of the Earth and that point gets bigger. So the further away from the Earth we get, the smaller the escape velocity becomes. And if we plot a graph of that, you get this graph here. And I've just marked here 10% of the way to the moon. And you can see that the escape velocity is it's more than half, less than half of what it was. So you may think, well, great, okay, well, let's just move a bit further away from the Earth and then try and throw our tennis ball, our cricket ball, whatever it is, up into space. Well, the highest a jet aircraft has ever gone is 37,650 meters at the time when I recorded this. So we do the calculation, it works out the escape velocity rounded to 3 significant figures is 11.2 kilometers per second. It's the same. It's a small reduction, but it's not that much. So clearly, trying to get into space by getting something moving and then just letting go and leaving it is not the answer, because it has to be going so fast that we can't actually get into space that way. There was, in fact, at least one object I know of from the Earth that did manage to get into space. I think it was the first man-made object in space. And it was a manhole cover that was part of a nuclear weapons test in the United States. They'd drilled this very deep well, put a manhole cover on the top, detonated a nuclear weapon underneath it to see what would happen if you detonated nuclear weapons underground. The manhole cover got flicked up into the sky going so fast when they analysed the film of it later and analysed the frame by frame where this manhole cover went. The manhole cover must have ended up in space. Don't know about you, but I find it quite disappointing that the first man-made object in space was caused by nuclear weapons testing. But there we go. So, okay, we can't just have kinetic energy being transferred to gravitational potential energy. There has to be another store of energy, because otherwise we can't go fast enough. So what if instead we used rockets? So a chemical energy store, turning that chemical energy into kinetic energy and gravitational potential energy as we launched our rocket up into space. And we're going to do some quick calculations here to see what happens, what the g-force would be. The g-force on you right now, if you're sat on the Earth, not accelerating anywhere, let's say it's 1. A g-force of 1. And you can go on funfair rides where you can get g-forces of 2 or more perhaps. The human body cannot survive, we think, g-forces greater than 9. That's the limit. Now you're going to see what happens now when we accelerate up to the escape velocity. And of course, as we accelerate, we're moving further and further away from the center of the Earth. So the escape velocity is dropping as we speed up. So at some point, we'll be going at the escape velocity. And to make the maths easier, we're going to assume a couple of things. Firstly, that we are traveling directly away from the center of the Earth, perpendicular to the surface. The second thing is we're going to assume the Earth is not rotating. I know it is, but let's assume it's not rotating to start with. And the third thing is we're going to assume our acceleration is uniform. We're not going to increase our acceleration up to some maximum. We're just going to press a button and we're off. We're accelerating from an initial speed of 0. GCSE physics equation that you'll see is this one. The final velocity squared of a body is equal to the initial velocity squared plus twice the acceleration multiplied by the displacement. That only works if we've got uniform acceleration. So that's why I've made that assumption. So if we have uniform acceleration, we've got this equation here. U, the initial velocity at the surface of the Earth, let's say it's 0. So v squared equals 2as. Rearrange it to get acceleration as the subject. So this is our acceleration. And the acceleration, if we accelerate at 9.81 meters per second, then that's a g-force of 1. If we accelerate at twice that, that's a g-force of 2, and so on and so on. Most we can withstand is a g-force of 9. 9 times the acceleration due to gravity. Now we had an equation for v in the last slide, the square root of 2gm over r. Well, let's substitute that into this equation. And the 2's cancel, and you're left with this, where r is the distance between the center of the Earth and that position where we have arrived at terminal velocity. Big R is the radius of the Earth, and s is how far the rocket is moved. So that's the height of the rocket. And if we substitute that into this equation, we get this equation here. And if we plot a graph of that equation, so a as a function of s, what the acceleration is on the y-axis and what the displacement is, or the height of the rocket, on the x-axis, it looks like this. Now, if you look at this, I've labelled the moon here. That's the height of the moon above the Earth. And this here, 0, is on the Earth's surface. And assuming constant acceleration, that's what's on the y-axis. And so 9g, which is here, is the maximum that the human body can survive. And so you can see, as soon as we've got a little bit further away from the Earth, we can switch our engines off. But if we only want to withstand 2g, we have to go a bit further. Actually, the scale's a bit small on this because of how far away the moon is. So perhaps we could look on a slightly closer scale. Here we go. So on this scale, I've labelled where the International Space Station is. The height of the International Space Station above the Earth. It's about 410,000 meters, 410 kilometers. 408 kilometers, roughly. And usually space is defined as 100 kilometers up. So it's in space, unsurprisingly. So if we wanted constant acceleration at 9g, we would have to accelerate constantly straight up much further than the International Space Station before we could switch our engines off and we're free. If we just went straight up with a non-rotating Earth and there's no air resistance and I put my motor on for 9g, I would have to go past the International Space Station before I could switch my engine off. If I switched the engine off too soon, I wouldn't have reached my escape velocity, and so I will fall back to the Earth. Well, hang on a minute, the ISS is in orbit. So it's because of those assumptions that we made, but let's just carry on looking at this. If you wanted to accelerate a rocket from the surface of the Earth just to the height that the highest jet has ever reached, and then switch the engines off and it escaped the Earth, then that rocket would experience 212 G. That small distance, the acceleration had to be so high. And I've labelled here 630 kilometres is actually how far you would have to go. Well, that's with those assumptions. Those assumptions aren't quite correct. One of the reasons those assumptions aren't quite correct is because we don't launch a rocket directly up. We launch rockets so that they gain some velocity from the Earth's rotation. It also increases the displacement of the rocket without actually increasing the height of the rocket, which means it can accelerate over a longer period of time, which means you can arrive at your escape velocity a bit later. So your g-force doesn't have to be as much. And by launching in this way, it also means that we are traveling in a direction tangential to the Earth's surface. And that's how orbit works. Something like the International Space Station, it is falling back to Earth, but it's traveling sideways at a speed so that as it falls, it never actually gets any closer to the Earth. We'll talk about orbits in a later video. So how do we get to that edge of space? How do we get up to the ISS? How do we get to the moon, which is what this topic's all about, exploring the moon? Well, we're going to burn fuel. We're not going to worry about trying to burn it all as quickly as we can and then gliding the rest of the way. We don't have to do that, but we can burn fuel to get up far enough. You remember from that graph, you don't have to get that far before we're at terminal velocity and we can switch our engines off. The problem is we are pushing our rocket in the air by burning fuel. That fuel is stored in canisters, in fuel tanks. Those fuel tanks weigh something. They have some mass. And if we want to get our acceleration up, then we want as little mass as possible. The smaller the mass, the bigger our acceleration will be for the same force. So we jettison empty fuel cans, empty fuel tanks. We jettison rockets that no longer are needed. The rocket breaks into parts. It's remarkably clever, the idea that the rocket itself, it's only the end bit that we really care about with the people in. All the rest of it is just there to get high enough and then jettison that part so that we've got less mass to continue to push upwards. Now, the equations used to try to figure out how much fuel you need and things like that, terribly complicated, and usually they would be solved numerically rather than trying to be solved analytically. During the space race, there were rooms full of women doing calculations, and the rooms, the women were referred to as computers, doing the calculations, because electronic computers weren't as fast as a room full of mathematicians were. There's a film about it. I think it's called Hidden Figures, but I haven't watched the film yet, I'm afraid. It's on my to-do list. So, okay, how does a rocket work? How a rocket works is actually really simple, the rocket itself. Planning the trajectory is the tricky bit. But the rocket itself is really simple. You heat up a gas. As the gas heats up, it expands, trying to occupy more space. That means it pushes on the rocket engine, and the rocket engine pushes right back. And that's why you see this burnt fuel pouring out the back. That's the exhaust. And the rocket is pushing that burnt fuel, that exhaust, back with exactly the same force that exhaust is pushing the rocket forward, upwards. And that's how a rocket works. It's time to move on to the next topic then, which is theories about the origin of the moon. The moon's not made of cheese, sorry. So the three theories you have to know are the capture theory, the co-accretion theory, and the giant impact hypothesis. The fission theory doesn't really get a look in, but the evidence for it is very similar to the evidence for the co-accretion theory, you'll see. And I've got a bit of a problem with this because a theory has to be tested and verified with data. So calling capture theory and co-accretion theory and fission theory theories, I don't think is correct. It's a misnomer. They're badly named. But let's look at the evidence for and against each of these theories. So let's start with evidence for the capture theory. This is the idea that the moon formed elsewhere in the solar system, just like asteroids and planets and everything else do. And it just happened to wander close enough to the Earth at some early point in the solar system, way back in the ancient history of the solar system, and the Earth just got captured. We're pretty sure that's what happened with Mars's moons by looking at the shape of them and their composition and comparing that to what's in the asteroid belt. But that doesn't seem to be what's happened with the moon. And the reason for that is that the moon's composition is very, very similar to the Earth's. And if it was a captured asteroid that formed somewhere else in the solar system, its composition would not be that similar to the Earth. Unless it formed near the Earth, it's not going to look like the Earth. So the second theory, the co-accretion theory, is the idea that the Earth and the Moon therefore both formed in the same place. Accretion means depositing matter together. So accreting means bringing together. And in the very early solar system, there was an accretion disk around the sun. And it coalesced on various places where the mass just happened to get a bit more dense. You would have the mass around it falling into that place. We call those places barycenters. And so the idea that the Earth and the Moon formed in the same region of this accretion disk, therefore they're made out of the same stuff, but just happen to form on two different barycenters, and that's why you've got the Moon and the Earth. And the Moon's tidally locked, so that's a good idea that maybe that's what happened. This little swirling patch of dust and gas that formed the Earth and the Moon. Well, perhaps actually that's why they're tidally locked, and perhaps that's why they're so similar in composition. Well, not quite, because if they were formed from the same patch of dust and gas, they'd have exactly the same composition, and they don't. There's small differences. For example, there's a bit more water in the rocks on the Earth than there is on the Moon. And actually, that's the same reason why the fission theory doesn't work. Fission theory is the idea that in the early formation of the Earth, it was spinning so fast that some of the matter couldn't stay on the Earth and got flung off into space and formed the Moon. And again, tidal locking can explain it. That's one way that tidal locking can be explained. But again, the composition of the Moon is not exactly the same as the Earth. It's close, but not exactly the same. So this is a theory that's currently accepted, the giant impact hypothesis. It's the idea that a very young Earth, a proto-Earth, prototype Earth, and some other planet called Theia collided. And we don't know whether Theia formed in the same sort of region of the accretion disk of the solar system as the Earth formed, or whether it formed elsewhere and just moved, because things do interact, these planets and other bodies move and interact with each other, and fell towards the Earth or got flung out towards the Earth. Not really sure about that. But there was this collision way back in the ancient history. The Earth was still molten at this point. And when Theia collided with the Earth, huge amounts of energy were released in this explosion. So much so that the two bodies combined. But they didn't stay combined. A bit got flung out because of conservation of momentum. So they kind of got stuck together and a bit carried on and got flung out. Now, because they were in the same place at some point, we can perhaps use that to convince ourselves that because of conservation of angular momentum, that's why there's tidal locking. Although there's other reasons why the rotation of the Moon slowed down to match its orbital period. And I think I've spoken about them in a previous video about the Moon. If this is the correct theory about how the Moon was formed, then we would expect the composition of the Earth and the Moon to be very, very similar. Very, very similar. But they don't have to be exactly the same. Denser material will have sunk. Less dense material will have floated. So as Theia crashed into the Earth, the densest parts of the combined mass of the Earth and Theia together, the most dense parts would have stayed on the Earth. The less dense parts could have been flung out. And that's why there'd be slight differences in the composition. There's also minerals on the Moon that cannot form unless you get really high temperature. I mean really high temperatures. Temperatures that you could get if a planet-sized object collided into an Earth-sized object. And you can't get those high temperatures in other sorts of situations. So where are those minerals on Earth? Well, because of weathering and things like that, those minerals, there might be trace amounts somewhere. But not in the amount there are on the Moon, because there isn't that weathering on the Moon. No atmosphere on the Moon, or very, very sparse atmosphere on the Moon. So it acts like a time capsule to look at what the surface on the Earth might have looked like billions of years ago. And that is everything that we wanted to cover in this video. Spent a bit more time on 9.4 looking at rockets, but in particular looking at escape velocity. It's all good physics. I enjoyed it. And if you're interested in this series and you want to be notified when there are more videos of this series that come up, then please subscribe to this channel and ring that little bell and you will be notified.